Hi there, my name is Adam Boxer, and I'm here to talk to you about embedding equations into the curriculum as part of the CogSciSci in the curriculum summer CPD bonanza. Before we get started, a little bit about me. If you don't know me, I'm the head of science at a school in North London called the Totteridge Academy. We are, we're a very different, remarkable school, and as a department, we're trying new things. And this is one of the things that we are trying in terms of our equation work. I'm also the managing editor of CogSciSci. If you don't know much about CogSciSci, I'm not really sure how you found this, to be honest. But if it was passed to you by somebody else, we are a grassroots collective of science teachers looking to introduce cognitive science into their classroom. We're now close to 2,000 members, something like that. We do blogs, we do CPD, all sorts of fun things. We'd love for you to get involved more. This video should link back to the CogSciSci page where you'll find loads of stuff. We've got resources as well, free resources for everything. That always tends to be the most popular stuff we've got. I'm also part of ResearchEd, which is an amazing organization. If you don't know about it, again, it's grassroots and it's dedicated to evidence-based practice in the classroom. You can get hold of me on Twitter at AdamBoxer1. You can email me anytime at adamboxer1@gmail.com as well. What are we going to be doing today? We are going to, so I'm just checking, yes, it's definitely recording, great. Okay, I do not want to do this and then find out I haven't been recording. What we're going to be doing, come on, click. There we go. End of slideshow. What the hell? It's not a great start, if I'm honest. Can I just quickly, right, what I'm going to do is I'm going to pause the recording. Right, there we go. So that was a terrible start, and I'll explain why it was a terrible start in a minute. So first off, what we're going to do today, we're going to look at what makes equations and the teaching of equations hard. We're going to look at a long-term approach to teaching equations. So not just something that takes place in one class at one moment in time, but something that spans, 2, 3, 4, 5 years. We are going to look at, from that model, then what you do in the class across 2, 3, 4, 5 years. There are two notes, okay? The first note I wrote on the slides, the second I didn't write. The first note is that this is currently speculative in the sense that the stuff I'm talking about are my ideas of where I want to go, and we're not fully there yet. So you're not going to be able to email me and say, oh, Adam, can I have the fully complete scheme of learning that you have for equations in science according to the presentation that you did? Because this is an ongoing process. This is kind of the philosophy, this is kind of the end goal, and in a few years' time, hopefully I'll have a finished package. The second note is that I have a newborn at home, and across the last 48 hours, I think I've slept about 6 or 7 hours, which is why I managed to start this presentation quite so badly. So if I do have any kind of errors or hiccups, please let me know. I will also be regularly sipping from my energy drink. Thank you. And a desperate bit to keep myself awake. I guess a third note is that I've got no idea how long this is going to take. So I guess just buckle your seatbelt because I think we're going to be in for way upwards of an hour. I'm recording this on Zoom, and Zoom is very temperamental in terms of when it decides to cut me off. So I might get cut off at 40 minutes, in which case I'll just start a new recording, but hopefully we'll just manage to plow through. All right, let's get started. Right. Where I want to start from is talking about challenge. So challenge is really important to me, and it's the word that I use to, and my department uses to describe difficulty, how hard something is. And we know that equations are really challenging to teach. We know that they're challenging for students to learn. We know that, they come up as it's a classic topic, when teachers are like, oh, I don't know how to do these equations. How am I supposed to teach equations? And the kids are always like, oh, I hate these damn equations and all of that. So, what I want to do in this session is try and break down what is it actually that makes these things difficult. First thing is just remembering them generally. So there's like 30 equations or whatever the students need to learn. And just anytime we're saying to students, you need to learn this thing off by heart, there's always going to be an associated challenge there because it's not like you can have a vague idea of what the equation is. If you don't get the things in the right order, it's just not the right equation. It's just wrong. There's search for the correct equation. So that word search is what I'm going to use later on as well. So search is where you're given data and you need to figure out what the correct equation is. So you search through a bank of equations. Now you might have those equations on a sheet and they might be provided to you by a teacher. You might be in an exam and you've got the equations data sheet or whatever, or you might be searching through your memory, and that's going to be quite common as well. But either way, the word search is what's going to be important, and that is a difficult to demanding cognitive process, because essentially what you're having to do is you're having to match up information from the question with stuff that is elsewhere. Okay, identifying the data in the question. So where you've got loads of information in the question, is identifying which bits of that are going to be going into your equation. What is the data? Taking the data from the question and putting that into the equation correctly. So a lot of the time, like, students will get the previous step right, but they'll get this step wrong. So you'll say to them, okay, so what's the data in the equation? They'll say, oh, right, well, the mass is here and the force is there. And then you say, okay, well, put that into the equation. They'll just put the numbers in. It's completely the wrong place. So that is a separate and distinct item that, again, contributes to the challenge of the exam question, of the equation question. Converting any units is also difficult. So even when, basic stuff like seconds, minutes, students will either forget to do it or they get it wrong. And then when you get more complicated, so key stage 4, where you've got all the millis and the megas and the micros and all of that stuff, that's going to be difficult for the students too. Rearranging the equation then. So we're going to talk a bit later on about whether you do substitute then rearrange or rearrange then substitute. I'm not going to get particularly ideological about it, but however you do it, this is an item of difficulty. So if you put the information into the equation, you substitute, then you've got to rearrange. So that's going to be difficult. Or if you rearrange and then substitute, that's still something that the students need to do. It does contribute to the challenge. And then finally, this is the bit I think is going to be the most different about this particular talk, is about trying to understand what the equation actually means. A lot of students, you give them the equation, you practice the equation, and boom, 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 they can come out at the end of the lesson, they can do the equation, be like, well, okay, what does the equation mean? Like, what is the relationship between force and mass? Like, you think, if I've got something that's got a really large mass, and I wanted to, have a really high acceleration, what kind of force do I need to apply to it? And the kid's like, what are you talking about? Give me the numbers. Where are the numbers? Well, that shows they don't really understand the equation. They've built like an algorithm for solving the equation, but they don't understand what the equation means. Now, sadly, it could be that in an exam, they're still rewarded. But I mean, obviously, this is a curriculum discussion. So this is about like us trying to give our students the best of what's been taught and said, and trying to get them to really understand what's going on here. And then, of course, there is finally assigning the correct units to the solution, which has been mitigated a bit now, I think, because AQA changed it in terms of how they're going to ask for the answers. So I think I've got another point. Yeah, so significant figures and decimal places, so they now put that towards the end of the answer as well. So there's a little reminder there. But even so, like, it does contribute to the difficulty of the question, and I'm sure that in many cases when teachers are giving students these questions to answer in class, they're not paying particular heed necessarily to significant figures, decimal places, units, all of that stuff. So no, units probably, but significant figures, you don't often see, like in a Key Stage 3 worksheet, it'll say, work if the force is X and the mass is Y, what is the acceleration to 2 decimal places? It just doesn't often happen. So yeah, that's something we need to think about as well. Now, what I want to do is I want to take all of these things and I want to give them all a color. Hey, see, right, so I've given all of them a color. And the reason why I want to give them a color is because I want to illustrate diagrammatically what normally happens in terms of the way these are taught. So normally you'll take an equation like F equals ma, and boom, you'll do all of the things. So you've got your lesson on F equals ma, you might have done some lessons on force already, you might have done some lessons on acceleration. Great, now you're going to do F equals ma, and boom, you're going to do 1, 2, 3, 4, 5, 6, 7, 8, all of those 9 points, right? In that lesson on F equals ma, or even across 2 lessons maybe. But when you teach F equals ma, that's what you're going to do. Now, why is this a problem? So if if any of you have seen some of my stuff before, then you'll be familiar with this equation. You can probably just skip ahead in the YouTube recording now. If you're not familiar with this, this is how I kind of conceptualize and think about challenge and the contributing factors towards challenge. If essentially, you give works to students, right? If it's too easy, the challenge is too low, then they're not going to learn anything. Because like, why would you learn anything? It's too easy. Like, if I give my kids in year 11 just some simple addition questions, like, they're not going to learn anything because they know how to add. It's not adding to their knowledge. And then equally at the other end, if I give them work that's too difficult, they're also not going to learn anything, or worse, it might embed misconceptions and the like. So this is the way that I conceptualize challenge and the different contributing factors to challenge. And I wrote about it in the context of Bloom's taxonomy, which I think is not a good model for talking about challenge. I think this is a good model for talking about challenge. So essentially, you've got 4 variables. The first is task quantity. This is the number of things you give students to do. So if you give students 2 things to do, then that's going to be easier than if you give students 4 things to do. Content demand is the inherent difficulty of the subject material. I haven't really explored exactly what defines that per se, and it's probably down to a number of other things. But broadly, I mean, it's about abstraction, isn't it? It's about difference. It's about how abstract something is, about how kind of distance it is from your day-to-day experience. So, for example, I was talking on Twitter recently about flotation, right? So, she's a primary school teacher. She was talking about how her kids experiment with themselves. They find out which things float, which things sink, and all of that. And the content demand of that is pretty low. If I give a kid a plastic ball from a paddling pool, and I say, well, this sink or float, that's an easy question because it's really obvious. But then if I give them a really complicated shape or a boat with a specifically shaped hull, and I say, will this sink or float? And you need to start then thinking about abstract laws of flotation that took humanity 70,000 years to come up with. Well, the content demand of that is harder. There are some things within the course that are just intrinsically more difficult to understand. So I guess animal adaptations are fascinating, and I love teaching them. But they are easier to understand than say terminal velocity. I don't think that's particularly controversial. I find teaching ionic equations incredibly challenging, whereas I find teaching how to make a soluble salt from a base and an acid, the content demand of that is much lower compared to having to teach ionic equations. So that also affects the difficulty. So on the top of that equation, we've got task quantity. If the more things you need to do, the harder the challenge, the greater the challenge. The more demanding the actual content, the greater the challenge as well. Underneath, you've got prior knowledge. So prior knowledge is how much stuff I know. So if I were teaching ionic equations, if my students had a really, really excellent hold over ions and chemical equations and all of that stuff, then they're going to find it a bit easier because their prior knowledge is higher. If their prior knowledge is lower, so if they're not so strong on their ions and the formation of ions and their state symbols and all of that stuff, then it's going to be that much harder. A really good example here, I guess, is stuff like when you teach the atmosphere or life cycle analysis. The broader students' understanding of just chemistry generally, the easier those things are going to be. Prior knowledge really affects is possibly the strongest variable, but it's crucial to think about. And then finally, is support, is the things that you give students to help them along the journey. So I don't know, let's say you were doing life cycle analysis and you had a table of a whole load of common materials and how they're manufactured, right? So that's a really useful support to students as they do that work. Another support might be providing students with an equation. Right, so an equation sheet is a support. So you increase the prior knowledge, you decrease the challenge. You increase the support, you decrease the challenge. And that's important, but there's 4 variables here, and you can manipulate each one. And it's completely up to you as a teacher to think about, right, well, what one's high at the moment? Maybe I need task quantity to be high, so what I need to do is give them a really strong support. Or maybe what you're saying is that in this case, actually, I can really reduce task quantity because the students are working in a position where they don't have great prior knowledge, and I can't really give them a support. So, you want to manipulate those variables to kind of get the challenge to be in the sweet spot. Now, in terms of equations, if we go back, here, you've got 9 things. That's too many things, right? The task quantity there is really high, right? So to an extent with equations, the content demand is fixed, right? There's nothing you can do about that. Energy drink sip number 2. Okay, so the content demand is quite fixed. There's not much you can do about it. F equals ma is F equals ma. You can't be oh, I'm going to make this easier by turning it into a different equation. You can't do that. And again, you can maximize prior knowledge and you can give your students this support, but still, if the content demand is high, you need to try and reduce the task quantity as much as possible. And this diagram here shows that you've got loads of things going on. It's just too many things. Now, according to theories of direct instruction and explicit instruction, which again, if you don't know much about, if you go to the CogSciSci website, we've got a little tab at the top that has It's called the Go Bag, which has got loads of lists, a list of loads of resources and links to academic reading. But broadly, explicit instruction, which is about teacher-directed traditional teaching, which is what I'm an advocate of and what I do, is what's called didactic pedagogy or talk and talk, often in a derogatory sense, but according to the evidence, it's the most effective by miles. Essentially, what explicit teachers do is they break things down into the smallest parts. So they would do something that looks a bit like this. Right, so they take all of those equations and they break it down into little bits and spread out over time instead of just giving students a massive chunk of information, because they want to reduce and pull down the task quantity. What we do in reality, though, is something that looks a bit more like this. Year 7, boom, magnification equation, unit conversion, everything, boom. Power, boom, next unit, energy, next unit, speed, everything, and then pressure, and then on and on and on. You might do more later on. I'm not talking about you wouldn't do miles in year 7. What I'm just illustrating that over time, you're going to do these equations, but like there's no attempt to like break them up into the component parts. Maybe like within a lesson, but broadly you get your worksheet. The worksheet has all 9 of those components on it. Like you've got to do everything there because that's what it is. So what are the problems with that? One, there are just too many things going on at once, right? This is not how explicit instructors, explicit teachers can manage their classroom, because we are used to what we want to do is break it up into smaller bits, which means part of the problem, so one problem here is that it's just too difficult, the challenge is too high. Another issue is that there are so many areas at which point a student can make a mistake. If you've got 9 things that a student can go wrong on, and to be honest, each one even has subdivisions of where they can go wrong. So there's so many different places that students can get wrong. Like it becomes impossible to give feedback. I'll get to that in a second. So it's really important that students can know how to do X, but if you're giving them 9 items, right, even though they know how to do X, you're increasing the likelihood that they'll still make a mistake in X, even if it's something that technically they know how to do. Because essentially you've got the high prior knowledge, which is at the bottom, which is great, but because the task quantity is so high, the challenges are going to be so large that even the stuff that you think they know, or that they definitely do know, they're still going to get wrong. And the key one here is that feedback becomes utterly impossible. That you have like these classrooms where like you've got 30 kids and they're all making 30 different mistakes, and you're having to hop, and it's incredibly stressful. And as a teacher, you also want to be managing your own task quantity. You don't want to be responding to 30 different mistakes. You want to arrange things so there is a much more limited range of mistakes for your students to make, so that you can immediately say, oh, that's a mistake you made. This is where you went wrong. Let me help you. You can't do that if they're practicing so many different things at once. and finally, they just learn less. Like those essential little bits don't get drilled enough. So over the long term, students aren't going to learn anything unless they get the chance to drill, which is practice. And essentially by doing so many things at once, doing these 9 things at once, you're going to stop them from being able to practice each of those individual things, and they're just going to learn less over the long term. Now, don't get me wrong. That doesn't mean that this way of doing things is dead right. Okay, so remember, I counterposed this one here, which is what we actually do, with this one, which is maybe what we should do. But actually there's a problem with this one as well. The problem is it's not feasible, right? How can you, okay, guys, I'm going to teach you about this equation called F equals ma, but I'm only going to teach you about the units today. And then in the term, I'm going to teach you about how to take data from a question and put it into the F equals ma equation. Like it's just not practical. It's just not the way it's going to get done. But more importantly, you fail to see the wood for the trees. Part of being an explicit instructor is not just taking that quantity and chopping it up into small bits, because you've also got to have a narrative. It's got to make sense to the kids. And if you chop things up into such small pieces that it doesn't make sense, like their knowledge isn't going to be grounded in anything, and it's just going to feel piecemeal and bitty, and the whole thing falls apart. The whole point of the challenge equation is that you've got 4 variables. You don't necessarily want to reduce your task quantity as much as possible. Sometimes you want to keep it at a certain point. Like take, let's say you're teaching, the various energy transfers in a coal power plant. Sure, you could do, right, today we're going to spend half an hour looking at how coal is burnt. Okay, half an hour's done. We're now going to spend half an hour looking at how the energy from burning coal heats up water. And the kids are like, what is going on? Like, what's the story here? you've got to explain to them, this is what happens. I start with coal, I burn the coal, I heat up the water boils, the water turns to steam, the steam turns the turbine turns the generator, the generator dumps energy into the national grid. You know, that's a story that like grounds the whole thing for the students. That's the woods. You know, the trees and the individual parts, but sometimes, excuse me, you really got to give the students the woods. And if you don't, then it's not grounded in anything. So maybe this approach isn't great either. So if you don't want to reduce the quantity this much, what else can you do? Well, we've still got 3 variables left. We've got support, prior knowledge, and content demand. And what we're going to do is I'm going to kind of, you know, this is I'm not going to refer to this equation every single time, but broadly, this is kind of the framework that informs my thinking here. So what we're going to do instead, we're going to look at something like this. I'm just going to let you look at that for a minute while I have power sip number 3. Essentially, what I'm trying to do is say that, and this is just schematic, right? What I'm trying to do is say that you want to look at your whole curriculum. Say, right, these are the equations I'm teaching, and this is when I introduce them. Let's do magnification first. Like, what do I want to actually do when I do magnification? Do I want to do decimal places and significant figures? Probably not. Do I want to do rearrangements here? Well, maybe not. That depends on my curriculum. But the idea is that you kind of build that up over time, and you kind of look at the skills that you want to teach and decide when you're going to teach them and what's manageable for your students, and carefully balance the fact that you don't want to introduce too many aspects or skills as colored chunks that we looked at one time, but also you want the equation to like make sense to students. You want it to be meaningful. Excuse me. I've also got really horrible cold. My daughter had a temperature over the weekend, not the virus, fortunately, but she did manage to pass on the colds to all of us, which is great. Okay, so what I'm going to do is I'm going to reorder the contributing factors into a more kind of sensible sequence that you could theoretically break up across a curriculum. So we're going to start with the recall of the equations generally, then the understanding of what it means, unit conversions, data in the question, data into the equation, rearrange the equation, units, significant figures, decimal places, and then finally search for the correct equation. And again, how and where you decide to slice these is kind of up to you. And again, like I said, it depends on your curriculum and your students, but I think this is a sensible route to slicing things up. You could swap 8 and 9, really, because search for the correct equation can essentially happen after students have learnt more than one equation. So once students know 2 equations, they can do search. Whereas significant figures, decimal places, we'll talk about later, but you might want to leave that until your maths department have broached the topic. Okay, and what I'm going to do is I'm going to break down each of these, and I'm going to give some ideas about how to maximize your kind of pedagogic effect when it comes to each of these. So recall equations generally is just about brute force. It's just about like recall, retrieval practice. But what I personally have found is that whereas teachers are really good at embedding declarative clauses into their retrieval practice, like, you know, in many classrooms, you know, teachers will often ask, what's the word equation for photosynthesis? You know, you teach equation for photosynthesis in the first term, and then in the second term it gets asked again, third term it gets asked again, it becomes part of the routine. But equations don't often. They tend, on average, in general, more to be like one-hit wonders, where like you do it once and then that's it until your end of year or end of term exam. What you need to do is you've got to embed it into your day-to-day retrieval. Like the students have to have the opportunity to be asked to retrieve just the equation. Like forget about using it or interpreting it, just what's the damn equation. They've just got to have that as part of their day-to-day retrieval practice. You add that into your mini quiz at the start of your lesson, which a lot of teachers will be doing. And again, it's a central plank of explicit instruction, starting the lesson with a recap or review of previous learning, and then doing regular reviews. So give me a second. Power sip number 4. I've run out now, which is a disaster. Oh well, these things happen. You can use an online platform, so like Carousel. If you've not heard of Carousel, I'm going to be completely shameless. Carousel is a online platform that I'm in the process of building with some wonderful tech developers. And essentially what it will be is you'll be able to upload a question bank. So 50, 100, 150, however many questions and answers that you like, and set those questions to students to do at home. And they type in their answers, and there's lots of self-assessment, there's automatic marking and all that stuff. You know, look, you can use other programs as well. You know, I guess Quizlet, Anki, Quizzes, Educate. I'm giving free advertising to my competitors here, but you know, look, I don't want anyone to be picking a particular program just because it's one that I've said you should do. You should pick the one that's right for your kids, right for your school. Carousel is one that's upcoming, and it's one that I happen to own. Okay, but it's got to be part of your like day-to-day regular culture. Cool. That's number one. And to be honest, that's the most straightforward. It's just about sitting down and saying, right, well, how am I going to embed it into my day-to-day retrieval and into my culture? You know, you might decide that, you know, in languages they do vocab quizzes, right? So why could you not do an equation quiz? Like once the kids have learned 10 equations, boom, every week you've got equation quiz. You know, you're going to give you 10. It will only take 5 minutes, right? Because it doesn't take more than 30 seconds to write the equation. So you know, there's something there. There's also you know, there's also cause to be optimistic, like a really tentative glance at EAQA, so, or whatever platform you use for analyzing your school's exam results, will probably show you that when it comes to recall of equations, a lot of your students get these questions right. So there is cause for optimism there. Okay, what's next? So we've now done part one, which is recall of equations generally, which means we are now up to part two, which is understanding what the equation actually means. This is where things get a bit fruity, because I do things here very differently to the way you might have seen them being done before. And what I'm going to do is I'm going to swap over to my visualizer. But what I'm doing, I'm just going to quickly pause the recording. All right, with any luck, you should now be able to see my visualizer. I do recommend that you get a visualizer. They're amazing, amazing tools for helping you work with your students and to kind of carefully model and break complicated things down. And what I'm going to do is I'm just going to take four example equations. There's that cold again. I'm going to do this a lot quicker than I would in class. But I'll show you the kind of the process of how I model these equations and how I try and teach students to understand what's going on. So magnification, I tend to use a series of diagrams where I'll say, let's say I've got a tiny, tiny object, that big. And this tiny, tiny object is 1 millimeter in size. It's really, really, really small. And I put that object underneath my microscope. And I look through my microscope, and now it looks 10 millimeter in size. By how many more times is it bigger? So it is 1 millimeter. That's how big it actually is. I look at it in the microscope, and the microscope makes it look 10 millimeter. Discuss as class, and students say, oh yes, that's 10 times bigger. If it's gone from 1 millimeter to 10 millimeter, it's 10 times bigger. We call this the magnification. And I might break that word apart and say the magni bit means big, or great, and ification means to make. Okay, so magnification is about making something bigger. It doesn't actually make it bigger. It's not like it's physically stretching it. It makes it look bigger. And I'll do a series of these different diagrams. I might do one for 1 millimeter and 10 millimeter. I might do another one for, say, 100 millimeter. And I'm going to use really nice, easy numbers so that students don't need to go crazy with mathematics and go, oh, right, that's 100 times bigger. That's pretty easy. I might do it 5 times bigger, or 20 times bigger, all of that. And sorry, there's that cold. Where was I? It's July the 27th and I've got a stinking cold. Such is life. I blame climate change. So where was I? Yeah, so essentially what you're doing is you're just making it like super visually obvious and clear to students what is going on. Now notice that I don't have any equation here at all. Now I will eventually make an equation, right? Because what I'll do is I'll say, well, I'm going to call this the actual size, and I'm going to call this the image size, and I'm going to call this the magnification. And what I'll do is I'll say actual size times my magnification equals the image size. See? Because I'm doing 1 times 100 gives me 100. Right? And I'll do a series of examples that just illustrate that point. And I've therefore derived the equation, shown them where it comes from, and I'll use this form. This is the form of the equation I use. And I know that all the biologists are like, oh, it's not the way to do it. It's magnification is image over actual. Yeah, that's fine. Right? But you know, image over actual is like really difficult to understand unless you're like really au fait with ratios. This makes perfect sense because like, oh right, I times that by that and I get that. That's like super obvious. So this is the form of the equation that I use because I think it's more intuitive. I think it's easier to understand. This diagram, use of this diagram is also really great for eliminating a misconception about focus and magnification. So, you know, I might say that, you know, that if I start with an image that looks like this, and I turn it to an image that looks like this, right? And I'll say to students, why is this not magnification? And they'll say, well, because it's the same size, right? All I've done is I've made it clearer. So I call this focus, not magnification. And that's a really important point, especially with the wheels, because the focusing knobs, the students think that if you move the lens up and down, that's about getting like closer or further, because that's like what a zoom camera does, I guess, or when you walk closer to something, it looks bigger. We're not going to get into the comedy of that sketch now, but broadly, you know, you can use the same set of images to illustrate the principle. And you say that, look, this is not magnification, they're the same size. It's just going from one being fuzzy to clear, so we call it focus rather than magnification. So hopefully that makes sense in terms of the way that I derive and use that equation. That might take me half an hour in class, you know, and I'll give students once to practice, and they can go backwards and forwards from image to actual, from actual to image, and all of that stuff. And through that, they're gaining a better understanding of the word magnification than if I just like mention it, talk about it for a couple of minutes, and then give them the equation and start teaching them how to use it. It's about laying the foundation of understanding there. It's increasing that prior knowledge, and I guess to an extent it's maybe even lowering the content demand, because then when you go on to the equation, the content feels less demanding because it makes a bit more sense. Power is next. Interesting. Where do I start with power? Okay, so for power, my students already know loads about energy and energy stores and energy transfers and all of that. So I might take a really simple example. Let's say I've got a battery. So I might draw a battery like this, and I'll draw a motor. So I like using the example of motors because with electricity and the new, you know, the IOP model, I don't want to use a light bulb because the way it transfers energy to the room doesn't really have a store. It's kind of complicated. I mean, it does, but year 7, like, I just want to keep it simple. So here I've got the motor that's just turning around, and actually often I'll use the example of like a desk fan, not a desk fan, one of the hand fans, you know, with the little battery in it. So I've got the battery, and then I've got the fan turning around, the fan or the motor, whatever, turning around. And I'll talk about the chemical store of the battery, and I'll talk about the kinetic store of the fan, and the pathway or the transfer is electrical working. I would write chemical with the students. I'm just going a bit quickly for you guys. And what I'd do is I'd talk to the students and I'd say, right, well, my battery is storing energy, okay? Now, they already know about energy and how to measure it. Well, not how to measure it, but how the units that it's assigned. Now, you know, let's say my battery stores up 100 joules of energy, and I turn it on. Now, does that energy all immediately go over there? That immediately you go from 100 joules here to 0 joules here and loads of energy there, 100 joules over there. Like, does it immediately go? And you can talk about that as a class. You could have your fan. You could say, well, you know, what is happening? And the students would say that, you know, it is slowly going down. You know, a model that you might use. You know, I know a lot of people are really kind of finicky about their models that they use for energy. But let's say you've got a model that has energy like here and then energy like here, and the energy is going from here to there, but it's not going immediately. It's taking its time. You know, slowly the energy is going from here to here, and eventually that battery will run out of energy and it won't have any energy left in it. It won't be storing any energy anymore. The speed at which that happens is called the power. It's called the power of the battery. So if the battery has a high power, it does that really quickly. And this goes like that. If it's got a low power, it does it quite slowly and it goes like that. So the power is about how quickly it goes from here to here. And actually what I'll do is I will teach my students what a watt is before we even start anything. And I say, right, so power, and I'll write a definition, is about how quickly. And I know the physicists are going to be like, well, it's a rate of change. Yeah, fine, fine, fine. I'm talking year 7 before you've even got to the equation, right? So it's how quickly the energy is transferred. And you notice, right, the reason why I've done it like that is because of task quantity. How many new things am I introducing in this definition? 2. 1, power, and 2, how quickly, right? But how quickly is super easy to understand. So in reality, so prior knowledge of how quickly means is quite high because students know what quickly means. If I said it's the rate of change of energy transfer, or you know, not the rate of change, but the rate of energy transfer, right, or joules per second, then that doesn't help me at this point. I'm building up to that point. If I want to introduce something new, power, then I want to use things which are familiar. They're familiar with transfer, they're familiar with energy, they're familiar with the idea of how quickly. I then want to say we measure it in watts, or W. And I would say 1 watt means, and I won't say equals, because again, I want to keep it like really concrete for them. 1 watt means 1 joule every second. 1 joule every second. And I ask students to write that down. And I say, okay, well, let's say something has a power of 2 watts. How many joules is that every second? And students will say, oh, that's 2 joules every second. Brilliant, well done. And if I say, okay, let's say I had one that's 4 watts or 5 watts or 10 watts or whatever, and we do again the same thing. How many joules is that every second? Brilliant, well done. Okay, so let's say, and I'll go for an example, and I'm going to use a model that will look very similar to the magnification one. And I say, let's say I've got a toaster, right? This looks like a toaster, right? Is that a toaster? There we go. There's my toaster. And I put my bread into the toaster. And let's say my toaster is 800 watts. Cool. Okay. All right. So how many joules does this transfer every second? And I wait. And I see most hands go up. And I see there's some students who haven't put their hand up. And I say, wow, you know, what's the answer? How many joules is that every second? So, oh, I don't know, sir. I said, okay, well, why don't you look in your exercise book, right? What does 1 watt mean? It means 1 joule every second. So if I have 800 watts, what does that mean? It means 800 joules every second. Brilliant, bravo. Okay, so that 800 watts means it's transferring 800 joules every second to the bread. Let's say, right, I left that on for 10 seconds. So remember, 800 watts means 800 joules every second. By now, by the way, some hands are going up already. Saying 800 watts means 800 joules every second. I leave it on for 10 seconds. How many joules go from the toaster to the bread? And I let them think, and then the student will put their hand up and say, 8,000. I'll say, how'd you work out? You do 800 times 8. Brilliant, well done. What I'll do here sometimes is I'll say, well, let's say I broke this up into 10 seconds. So each of these was 1 second. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'll make my line a bit longer. 10, right? So each of these was 1 second, 1 second, 1 second, 1 second, 1 second, 1 second, etc. Now, if it's 800 watts, right, that means I've got 800 in each of these. You probably want to draw this a bit bigger, okay? So, you know, you can imagine I'm drawing it bigger, right? I can't be bothered right now, right? So 800, 800, 800, each of those seconds is giving me 800. You then add all those up, then you'd get 8,000 joules. Bingo, look at that. So 8,000 joules is what comes into here. Because each one of those seconds represents 800 joules. So that's one way of doing it. Another way of doing it and this is this only works if you're like if you really thought it through in advance, is you do the second as like a time, like a clock face, like this. So you say, right, well, I've got 10 seconds, okay? Because this is, I guess, a bit like a clock or a watch, right? So I've got my first second, second second, third second, fourth, fifth, sixth, seventh, eighth, ninth, and there's my 10th. And in each one of those, I've got 800 joules. Like that, and so on. Okay, so in total, how many joules do I have? Well, you just count them up. I've got 10 of them, 800 joules times 10, 8,000. So I get, and the bread increases by 8,000 joules into its thermal energy store. Voila. It's pretty straightforward, but what I'm doing is I'm trying to model exactly what's going on so that my students aren't like, okay, well, I'm just going to chuck these things in and do an equation and like, I guess it works and I get the answers. I don't really understand what it means. To really getting to the guts of what 800 watts means. You can then do a whole series of examples. So I teach my students the word device or appliance. So I don't have to say a toaster or an iron or a kettle every time. And I just say, right, well, let's say you've got something that's let's use a different number to 8. I say let's say you've got 50 watts and you leave it on for 5 seconds. How much energy have I transferred? And again, you just do the same thing. You say 1, 2, 3, 4, 5. So 50, 50, 50, 50, 50, and sorry, and that's it. But you want to make sure, by the way, that you do joules here, okay? Because a classic misconception will be then thinking that this is the same thing. It's not watts, it's because this is by time. So I'm going to say, right, that means I'm doing 50 joules every second. That's the first second 50 joules, the second 50 joules. And the students are like, oh, that's really obvious. It's 250 joules. Brilliant. And again, you can use the round thing, you can use the line with the segments, whichever way you like it. But the idea is that you're modeling what this equation actually means. And then again, exactly with the previous, you have your device. So let's say you do the same example. You've got your 50 watts. You've got your time of, what did I say, 5 seconds. And then you've got your energy being transferred. Let's just call it, sorry, 250 joules. And you can say, right, well, this is called the power. This is called the time. And this is called the energy. How did I get from here and here to here? I timed them together. I did 50 times 5 gives me 250. Ta-da! And again, this is the form of the equation that I use. P times T equals E. And again, the physicists are going to be like, well, but it's not that, right? It's not the canonical form of the equation. Okay, fine. It's supposed to be P equals E over T. Fine, fine, fine. This is easier to understand. So this is the canonical form that I use and that we use in our curriculum because it makes more sense. It's easier to appreciate, it's easier to understand because of the way that we model it. If you can come up with a different way of modeling it that makes the same amount of sense and that slowly introduces the ideas, then absolutely fine. If you can't, then go with this one. Yeah, cool. What's next? Pressure. Okay, pressure, force over area. So again, I'll spend a lot of time talking about how, basically, I'll spend an entire lesson talking about pressure in general, which is just about like spreading out the force. But models that I might use involve something like a block like this. So this I borrowed from my 3-year-old daughter. It's called, you could call it, I guess a fancy word is a manipulative, something like physical that you can use to demonstrate something. And if you had one at school, you could write on it. I'm not going to write on it because my daughter will kill me. But what I'd say is, let's say I've got a block, right? That is, if your students don't already know what weight is, don't do pressure yet. Teach them what weight is first. And I say this has got a weight of, say, I don't know, 100 newtons, okay? Which means that it's pushing down on what's underneath it. And you could draw, a surface. So it's sitting on like a table. And it's pushing down with 100 newtons on that table, just like this is. Now the thing is, right, that 100 newtons is being applied through the whole surface here, this whole bit here, right? So if I put it like that on the corner, that 100 newtons is just going through the corner. If I put it like that, the 100 newtons is going on this bit. We call that the surface area. This surface has a certain size, and it's the area of that is called its surface area, and the force goes through this whole thing. And I tend to I've got a really nice drawing book. It's got really nice big squares, so it's centimeter by centimeter squares. So I'm just find a blank page. Here we go. Where are we? And I say, okay, fine. So let's say I've got my block, right? And it has a weight of, what did I say, 100 newtons? Yeah, 100 newtons. And I look underneath it, okay, and I draw that, what it looks like underneath, and it comes out as looking like this, okay, where each of these squares represents 1 meter, okay? So each of these squares is 1 meter in length and in height. It's a square. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Okay? If I've got 100 newtons and it's being spread out between all of them, because remember, right, there's no reason why there'd be 100 newtons coming at like one bit, like right here or right here. It's coming out evenly across the whole thing, like it's spread out across the whole surface, right? So what I would do is I'd say, right, well, if this is 100 newtons in total, each one, and I'd probably use a smaller pen. Let's see if I've got one. Will this work? We'll find out. And I'll write 10 newtons there. I think you can probably just about see that. What I'll do is I'll zoom in for you. Okay, focus. There we go. Hopefully you can see that relatively clearly. So I'd say that like that 100 newtons splits up into 10 newtons here, 10 newtons here, 10 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 there, and 10 there. Right, so in total, I've still got 100, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, right? But it's spread out across the whole thing. Now, remember I said that each one of these is 1 meter. So which means that that's 1 meter as well. And like, obviously, guys, this is not like a meter. This is much smaller. I'm just going to use a meter because those are the units that we use. We'll explain more later. Fine. Right, so each one of those is a meter, which means essentially I've got, if I were to kind of expand one of those, I've got a box that's got 10 newtons and it's 1 meter here and 1 meter there. Now you guys know from maths that the area of this is 1 meter squared, which means I've got 10 newton in 1 meter squared. If I look at the whole thing, I've got 10 newtons for every meter squared. So I've got 1 meter squared here, 1 meter squared here, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, which means that overall I've got 10 newtons per, which means like for every 1 meter squared. Scientists write this as 10 newtons per meter squared. This is called the pressure. 10 newtons per meter squared here is the pressure. It's about how much that force, this overall weight, this 100 newtons from this block is spread out across here. And if this is 100 newtons, I've got 10 here, 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 and each of those newtons, 10 newtons for every meter squared. You then want to do a bunch of other examples because, like, you know, this is really abstract. But again, like, I can't think of a better way to explain it to students. You know, the concrete examples are all very well. They're about like laying the grounds, but actually understanding what this means, I can't think of a better way to actually do it than saying, right, well, these are the meters squared that are involved. I've got this many newtons. And then, so that's how it works out. You'd want to do other ones. So you might want to do a box of, 3 by 3, so 9. Again, you want to use nice round numbers. So you might want to say, well, I'll use 90 newtons or 900 newtons or whatever, so that you've got nice, easy numbers to play with. Again, you're saying 10 newtons per meter squared here means 10 newtons in every meter squared. Okay. Now you can then construct your equation, because then what you're saying is that if you've got your force, and I want to get from my force, which is 100 newtons, and I want to get to my my pressure, which was 10 newtons per meter squared. How did I do that? I divided it by these 10. So I divided it by the surface area, and that gave me the pressure. Again, in constructing it in exactly the same way, I did 100 divided by the 10 to give me 10 newtons per meter squared. And I guess actually I'd probably want to start it again and lay that out a lot more neatly, a lot more intuitively. But broadly, I'm hoping by now, because this is a third example, you're getting the idea that I start with a really like concrete, obvious, simple example that makes intuitive sense, then turn that into an equation. And again, with this one, you definitely want to do a bunch of examples. Okay. Cool. What's the last one I said? Specific heat capacity. I included this one because it's more complicated. Specific heat capacity is, oh man, it's really difficult to explain what's going on. But essentially what you want to do is you want to say, like, let's say you want to start with, again, really concrete example. You say, like, let's say I've got, a beaker full of water, and I've got a beaker full of, say, oil. So you might want to say this one's water, this one's oil. And you might say, right, well, what I do is I heat these up. And I put, like, I don't know, 10,000 joules into this one. And I put 10,000 joules into this one. And in each one, I put a thermometer. Do they show the same temperature? You could demonstrate that if you like, or you could just say, no, they don't. They don't show the same temperature. Why is it they don't show the same temperature? And a kid might say, oh, well, there might be different amounts. Okay, that's fine. We'll hold on to that for a minute. But, why else? So, well, what is water? What is oil? Yeah, you're right. So water and oil, they require a different amount of energy to change the temperature. You could then move it over. Say, right, well, if I've got this much, let's say I'm just doing water. And I've got another, I've not aligned that, which is really annoying me. I'm going to blame it on the tiredness. Sorry, I'm going to double blame that on the tiredness because it's an error that I didn't want to make. Give me a sec. So while I was narrating my incompetence, I made a further mistake. Okay, so let's say this is water. And then you have another beaker that you only half fill up with water. And you say, okay, well, I've got 10,000 joules here. And I've got 10,000 joules here. And I put a thermometer in both as before. Like, are they going to go up by the same amount? Are they going to go up by the same amount of temperature? By the same temperature? Oh, well, no, I don't think so, because but they're the same thing. Well, but there's a different amount of them. Great. So fine. That means there's got two different variables here. We've got the actual substance itself. So is it water? Is it oil? Is it metal? Is it wood? Is it plastic? Whatever it is. And we've also got the amount of stuff there is, which we will refer to as the mass. So let's say I take a substance, right, that has a mass of 4 kilograms. Now, I want to increase its temperature by, say, 1 degree. I want to make it hotter by 1 degree. So I need to heat it up. So what I'll do is I'll draw that out like this, and I'll split it up into its 4 kilograms. So this is 1 kilogram, that's another kilogram, that's another kilogram, that's another kilogram. And I still want to increase it by 1 degree. Let's say I do an experiment, and I find out that each of those kilograms requires 10 joules. Again, I'm using my pencil here. I really should have brought a biro, but I didn't. Sorry. So I've got 10 joules here, and I've got to get 10 joules into there. I've got to get 10 joules. That's what I find out. Or I tell you what, you could do better. You could say, let's say I find out, and obviously I brought a pencil that doesn't rub out particularly well. Let's say I find out that I need to put in 40 joules of energy. I need to put in 40 joules of energy. Well, that means that I put 10 joules into this kilogram, 10 joules into that kilogram, 10 joules into that kilogram, and 10 joules into that kilogram. What that means is that for each kilogram to go up by 1 degree. And remember, you'll then have to kind of, I guess, preempt and say, well, then why doesn't it go up by 4 degrees? And you say, well, because it's the whole thing that you're looking at. I don't know, maybe that's not a good way to do it. I mean, I'm not really sure what the alternative is, to be honest. So you've got to, you can talk about averages if you like. I guess you could say that, right, well, if I wasn't putting this one up by 1 degree as well, I guess maybe if you started with one that's got only 2, and you say, let's say I only put this one up by 1 degree, right? Then on average, it's only half a degree. And I did 0 here, then on average, it's 0.5. I guess it's a good way to prove that each one has to be going up by 1 degree, unless I'm putting this one up by 1 and this one up by 1. Okay, so that's one way to do it. So for each kilogram to go up by 1 degree, I need 10 joules. So 10 joules for each kilogram to go up by 1 degree. We could say that that is 10 joules per kilogram degrees C. And you would call that then the specific heat capacity, and you would write your definition of that as the amount of energy required to increase each kilogram by 1 degree. And then again, you would do a whole load of examples. And because you've got a whole load of variables here, you can do loads of different ones. You can make the math much bigger, make the math much smaller. You could say, right, well, I don't want to go up by 1 degree, I want to go up by 10 degrees. I don't want to, and then you can change the specific heat capacity as well. You can say, right, well, this one has a specific heat capacity of 50 joules or 100 joules or 9.8, or whatever it is. But you are 9.8 kilojoules, so 4 point, whatever it is, kilojoules per kilogram degree C. So what you're then doing is you're building up a picture and you're showing students what this specific heat capacity actually means. You then turn into, right, well, let's say I want to turn this into an equation. And you say, right, well, how do I work out how much energy, for this you really do want to go with the canonical version. So well, how do I work out how much energy from a specific heat capacity and from a temperature? So you do one, so you say, right, let's say I've got an object that's 6 kilograms. I want to increase it by 1 degree, and its specific heat capacity is 15 joules per kilogram degrees C. How do I work out how much energy do I need? So how much energy do I need? And the students will say, right, well, you just put 15 joules into each one, etc. You've got 6 kilograms, you've got 1 degree. So essentially you've done, so how much energy in total? You've got 6 of those 15s, which is 60 plus 6 times 5, which is 30. So you've got 90 joules total. Okay, fine. Now let's say I wanted to do the same thing, but I wanted to increase it by 2 degrees C. So the students will say, right, well, what you'd need is for each kilogram, you'd need 30. 30, 30, 30, 30, 30, which means you've got 30 times 9, 30 times 9, 30 times 6, which gives you 180 joules total. Well, hang on a second. What did you actually do there? What maths did you do? So, sorry, pull that out so you can see what I'm doing. What maths did you do? So, right, how do you combine this, and the, you might want to say that? How have you combined those to get that? Oh, well, I've just done that times that, which is the specific heat capacity times by the mass. There's 6 of them. So I've got this 15, or you can do the 15 times the 2, whichever way you prefer first, and then times the temperature. Oh, for God's sake, sorry, that should say mass. You've got the specific heat capacity times the mass times the temperature, and that gives you the energy required or the energy transferred. And hey presto, you've derived another equation. It's pretty straightforward that. I say pretty straightforward, it's pretty complicated, but again, to my mind, I can't think of a simpler way to do that. Now I've got, if you are interested, I've got a much longer, slower version of this, which is more student facing, where I've really thought through the examples that I use on my YouTube channel, which is Boxer's Shorts. So if this is a model that interests you, be like, well, hang on a second, there was a bit in there where you put a flaw because of blah, 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 then just have a look at that video, because there I really sat down for ages beforehand and thought about it, rather than right now where I am sleep deprived and fairly addled of mind. And again, essentially what you're doing is you're showing where those numbers come from in a way that isn't just, here's the equation, this is how we work it out, this is what it is. You're saying, right, well, I want to break it down. I want to show to you what's going on. What is this unit? What is this specific heat capacity? Cool. All right, I think I've done all that now, which means I can say goodbye to my visualizer. Actually, sorry, so let's go back to the PowerPoint and let's change the video. So you can now look at me. Here I am. I'm back. Okay, so what I'm trying to do is I'm trying to illustrate that there's for each of these equations. I think the traditional way of doing it is just saying this is the equation, or giving like a 2-minute introduction and saying this is the equation, let's do it. Whereas what I'm trying to show is that you can spend quite a long time actually explaining what the equation is, so that you are teaching for understanding. And so my guiding principles in general here are about moving from something that's really concrete, like a yellow block, or a toaster, or a fan, or like a specific thing that you're looking at under a microscope, and then moving to this abstract equation which describes what's going on, and because the point of the equation is that it's generalized. It can do it for any scenario. So whereas my little diagrams work for the particular diagrams I show, the whole point of the equation is that it works for anything. You can plug any scenario into the equation. And that is always, anytime you move to like a generalized abstract principle, that's always going to be difficult for your students to understand. I also always try and move from the known to the unknown. I try to demonstrate that more when I did magnification, when I did the power, that you're taking the things that the students do know and using that to go to the things that they don't know. So in the power one, the things that they do know, energy and quickly or time, and you use that to teach about power. So you isolate power as the thing that you really want to zoom in on. The same for the specific heat capacity example. Like, everybody knows what mass is, they know what energy is, they know what temperature change is, right? So you use those things to move to the specific heat capacity. What else have I got? Okay, so what I'll do a bit later on is I'll show you how you can check these things for understanding without using the equation. So before you've taught an equation, or how to use an equation, so how you can establish student conceptual understanding of what the equation will eventually mean, or what the relationship here means. Okay, so we've done recall of equations generally. We've done understanding what the equation actually means, which means we've only got 7 more points. Don't worry, I'll go a bit quicker during these because we are already about an hour through. Converting unit conversions, again, you've got to take a long-term approach here. You've got to decide which unit conversions you want your students to do, and isolate and teach each one, and not just chuck them in haphazardly and just have an equation. You have a practice sheet where suddenly students have got to transfer seconds into minutes, and they might be able to do that, but like, you've not modeled it, you've not gone over it, they're going to make mistakes, guaranteed. So a long-term approach might say, let's say you were doing magnification in your first unit. So you'd start with measuring image size, and you'd use a ruler. Right, you'd say, right, how do I measure this? This is, I want to measure the size of this. I'd use a ruler. Then you want to talk about conversions. So you might want to give students diagrams of cells and say, right, let's draw this. Let's measure its length in centimeters. Okay, right, how do I change that into millimeters? How do I change that into meters? Then give students practice on that. Then you do all the stuff that I did before about, teaching the magnification equation. Then later on, you're going to do power. That might be in your next unit. And again, you do the idea of power first, which is the diagrams I showed you with the toaster, and with the battery and all of that stuff. Then you want to do conversions of time as just entirely its own thing before you've taught the equation, right? And then you do the power equation. So by that point, students now have a good idea of power. They have a good idea of these unit conversions. You can then teach the power equation and intersperse the unit conversions. Another route might be that you do, so if we zoom in on the power bit, so you do your power equation as the first form. So in my, which in my system is P times T equals E. You then, so let them practice that. You then do some unit conversions, and you then do the first form again. So just P times T equals E, but with seconds, minutes, and hours as part of that practice set. You then teach the second form, you then teach the third form, and so on. So essentially what you're doing is you're saying, right, well, when exactly am I going to do these unit conversions? When's the right point? Because the second you introduce the unit conversions, you're increasing the difficulty because you're increasing the task quantity. You're increasing the number of things that the students need to do. They don't just need to do the equation, they also need to do the unit conversions. Give me a second. Okay, which means we've now done converting units. So we've done recall, we've done understand the equation, we've done the units. Identifying data, inputting data, rearranging, assigning correct units, and doing significant figures in decimal places, we can do all in one go. Because all of these things, let me move me out of the way, should contribute to one unifying method. And I'll let you just cast your eyes over that diagram for a sec. So each of these things, you can teach them individually, but to be honest, it might be easier to find one unified method or system or process that encompasses all of them. What are some popular choices? We collected a few a while back on the CogSciSci website. So if you go onto the website, we've got a blog article that's got the best way to teach equation. It's got links to further blogs that give specific routes to teaching those equations. What are those routes? So some popular choices is FIFA, which is from Gethin Jones, and that involves the formula. I think I stands for input, F I think stands for fiddle, I'm not really sure, I can't remember, and then A stands for answer. You've got the every method, which is from Tom Chiliman, where the E is equation, V is values, E equals something else, I can't remember. There's the Michaela method, which is on Pritesh Raitura's blog, which involves like highlighting stuff in the equation. And I can't remember the rest of the details. You've then got DeskUse, which a colleague of mine, Brendan Mahoney at TTA, came up with, and it's the one that we use. So DeskUse, the reason why we do it, this is going to sound completely mad, but at my school, we have these things called chants, and the math team use chants the most. And essentially a chant is like, it's a problem-solving method. So whenever you see a particular equation, a particular question, you've got a chant for that question. So what we do is we shout at the students, we say, if you have the data, and they shout back, you have no excuse. And that's their way of like remembering that this is what they need to do. So they write down the data, they write down the equation, they substitute into the equation, then they then calculate, and then do the units, and then the S stands for significant figures. So I know it sounds completely mad, but it works. So, and it's all good fun as well. So we shout the data. If you have the data and they shout back, you have no excuse. And again, it's like our way of holding them accountable. Like, oh, I gave you the data, you've got no excuse for getting it wrong. Where did you go wrong in the steps? And then literally just like last week, so Matt Ben-Yohai did a blog post where he advocated the rearrange first method. I'm not here to talk to you about whether you should be rearranging or substituting first, because different people have different opinions. Personally, we substitute and then rearrange because we found that to be a bit easier, and it's because it's more in line with our maths department, who are like really strong. Our maths department has the 7th highest progress rate in the entire country, so like we'd be mad to not do things the way they do things. But broadly, there are a whole load of different choices there, and each one of those should encompass all of those things. Okay, so let's just go back. So it should encompass all of these things here in the one method. Don't use triangles. I mean, we're past triangles now. We can do better. To be honest, if you look in Gethin's blog that's linked here, he explains why actually triangles are harder to use than the equation. If you're not, teaching the equation right, if you use a good method, it's not difficult, right? Whereas, however well you teach a triangle, it's still going to be harder than the most straightforward other methods that you use. It's also absolutely no good for a whole bunch of equations. Good luck using a triangle with specific heat capacity or kinetic energy. It's just like daft. And most students, I've never met a student who, once I've taught them like the DeskUse method, couldn't do it. Right? They can. So just don't use a triangle. I hate triangles. Triangles are banned. Right. So what I want to do now is break down. So within a lesson, how would you structure your question set or your practice set in order for your students to fully kind of like embed and understand this equation. And again, this is a process that works over time. So first you'd have a section. You have basically 1, 2, 3, 4, 5, 6 sections. The first is about understanding the science. You then have the 3 forms of your equation. You then have mixed forms, and you then have what I call search and destroy. And I've got a little diagram here that illustrates the challenge. So the challenge starts off low, and in each set it increases, right? That's what this shows, right? That it starts off low and then increases, and then it kind of resets and goes a bit lower. So if the kind of the width of this is about the challenge, so it goes a bit lower into the next section and then increases, and then goes a bit lower into the next section and then increases, then a bit lower, then increases, and a bit lower, then increases, and a bit lower, then increases, until by the end they're doing something which at the beginning would have been incredibly challenging for them. But because you followed this process, it kind of works out, and you've built them up to that level of difficulty. So what's this look like? So first you'd have understanding the science. So this is what I was talking about before. So before you've even taught the equation, so like what pressure means, what magnification means, those like diagrams. Here are some example questions that you could use. So that's one for power. But they don't need to know the equation to be able to do that. Remember, I said to them first, I teach them what means 1 joule every second. Can they answer those questions? Yes, of course they can answer those questions. They can sit down and do them themselves, and mini whiteboards, whatever, but they can do that. That's not a problem. And then you could do that. Again, like they don't need the equation for this, right? Implicitly, they are using an equation to be short, but they're not actually sitting down and using an equation. They're just saying, all right, well, I know that 1 watt is 1 joule every second. So if I've got 10 seconds and it's 40 watts, it's going to be 400. No problem, 400 joules, easy peasy. You can make these more challenging, more conceptual. So I've got, this is a really nice question that I like. Yeah? So this is a brilliant springboard, in my opinion, to really conceptually thinking about the difference between power and energy, that power has this linked aspect of time. You can't say more energy is transferred by the red car, because I could leave the blue one on for 10 minutes and the red one on for 1 second, and the red one is going to transfer a lot less energy. So it's about that aspect of time. And again, there's a really good way to like tease out that conceptual understanding before you even got to the equation. Here's an example for pressure. So you might want to get a shape like this. So this one isn't so illustrative that I use, because even though this face is shorter than this face, it's not obviously so, but you could use, say, this face. So you can say, right, well, if I put it on this face, is it going to have a higher or lower pressure than if I put it on this face? That second question is a beaut, because it's about understanding that the weight of the object doesn't change. It's just about how much that weight spreads out. So if that weight, so if it's sat on the big face and the weight is spread out across a bigger area, if it's sat on the small face, it's spread out across a small area. And then that's when you do all your, person in stilettos has a higher pressure than an elephant or whatever, that kind of stuff. And again, conceptual understanding. Here are some examples for specific heat capacity, which I'll let you read through. There's a spelling error in the second bullet point. So again, some like really nice questions there to tease out that conceptual understanding. And that bottom one is already starting to move towards an equation. Again, the more students can appreciate the mathematical relationships before you start the equation, in my experience, the better they're going to be able to then use the equation further down the line. Right, next up is unit conversions. So because if you've not, going back to now power, so power, energy, and time. So at this point, right, so once you've taught the concept, so just hopping back, because I know that I just distracted you by talking about other equations, but if we go back to our power equation, so I've taught them now the relationship between power, time, and energy in these diagrams, what it means, what watt is, what joule per second, all of that stuff. At this point, if my students haven't done unit conversions for time, this is when I would do it. So before we start on the equation itself, or maybe after first form. So I'd now teach the equation and how to use it. Let me move myself out of the way so you can see what's going on. Yeah, I then teach the equation how to use it. So again, I use energy equals power times time. That's the formula I use. And I would use, I use my desk use methods. So I'd say, right, we're going to lay out D, E, S, C, U, S. Write down the data, write down the equation, substitute all of that. When I'm teaching the first form, I make sure I follow an I, we, you structure. So I will do an example or 2 examples or 3 examples. We will then do examples as a class, which means either I'm taking responses from students about what I should be putting into my example, or I'm asking them to do one practice question themselves with their mini whiteboards or something along those lines, some way that they're not independently practicing yet. We're still kind of doing it as a class. Then once I'm happy, then they go off and they do their own practice independently. If they're working in pairs, like, they're probably going to learn a lot less. Or well, one member of the pair is going to learn a lot, the other is going to learn a lot less. But so I start with me doing it, then we'll do it all together. And then they do it themselves. It's about like gradually pulling back support. Okay, so if you think back to our equation, right? So their prior knowledge and support on the bottom. So at the beginning, their knowledge of how to use this equation is quite low. So my support is going to be quite high, which is why I'm doing it. Then their knowledge starts to increase, and I say, right, now we're going to do it together. And I'm going to pull back my support, and then I'm going to pull back my support more and more and more and more until they're ready to independently practice all themselves. Could do things like problem pairs. So this is borrowed from maths pedagogy. I first saw these in Mr. Barton maths book called How I Wish I Taught Maths. And essentially what you do is you have 2 examples side by side that are broadly identical or directly analogous, and then you would model how to do it on the left hand side. You can do this on a board, visualizer, wherever you like, and then students would do it themselves on this side. So this is a support, so it's basically a worked example, but it's side by side, so it's even higher. So again, you know, at the bottom of your equation, you want to keep that support really high at the beginning while their knowledge is low. Now again, you don't want to have them do this for every single question, right? If you've got 30 questions you want them to do, you don't want to do every single one. Me do it, then you do it, me do it, then you do it, me do it, then you do it. And the reason for that is because their prior knowledge is increasing. So as their prior knowledge increases, the support has to decrease to counteract and keep the challenge like a sweet spot. Multiple choice questions are really good here as diagnostics. So for example, if I've got how much energy is transferred in 30 seconds by a 10-watt device. So instead of asking, I might ask them to work it out, and I'll give them options for an answer. And I'll say A is 3 joules. And if the kid puts their hand up for 3, then I know they did time over power, which is no good. I say 40, which is they've just gone completely wrong. They've added these 2 together. Happens. 0.33 would be, what's that, 10 divided by 30. So I know they've done that that over that, which again is no good. And then 300, which would be the correct answer. And basically by doing it that way, then I can spot really easily where the errors were. So I won't say, work it out and say, right, well, the answer is 300. Put your hand up if you've got 300. Great, 3/4 of the class got 300. And the kid puts, and I say, right, well, what did you get? And he's like, oh, I got 0.33. And I'm like, how do you get 0.33? Right, and then I have to go think about it. This is like me preempting it and getting ahead of those errors. And then of course you might want to open it up for further mistakes. Like some kids will just like get it catastrophically wrong and do totally mad things. They might like turn this into minutes, and they might take one away from the other. God knows, they have remarkable capacity for getting things wrong. Yeah, and then so I'm now ready to go on to the use step. So just to go back, this is all kind of I and we. This is still a kind of a we example, and now I'm ready to let them go off and practice. I'll give them a practice set that looks like this. Really straightforward, not particularly complicated, not particularly wordy, but you can see that as time goes on, it turns into minutes here, right? So the challenge is maintained. I've got A, B, and C, which are basically very similar. So, okay, let me slow down, sorry. A is like that, and then B is very similar to A, which is great. I then swap that and that to maintain the challenge, because if I just keep them as what's then time, what's then time, what's then time, what's then time, the challenge doesn't change throughout the problem set. And if they've got the first one and the second one right, they're going to get the third one right. They're not achieving anything. So as they go through the practice set and their prior knowledge increases, I want to change the demand of the question by increasing, perhaps reducing the support, or by increasing the quantity of things they need to do. This one, when you just swap the numbers around, so in this one, it won't really make a difference because it's about timing them together. But for others, especially when you're dividing, it will make a difference. For me, this is about removing support, because essentially the previous questions are a support. So if you've done something 10 times and the 11th is the same as the previous 10, then those 10 are like a support. It's like an algorithm. It's something in your head that isn't really contributing to your knowledge. And it feels much more external. So by swapping them around, you're jolting students into having to think about it a bit more. So maintaining the challenge that way. You then increase for D, You then increase the task quantity because they've now got to do the question as well as do the unit conversion. And then again, another one, the same for the next. And then the final one is a different type of unit conversion. So what you're trying to do is you're trying to maintain the challenge the whole way through. If you've got a question set and each question is really, really similar to the previous one, then you're not changing the challenge. You're not going to. It's not a dynamic question set. Remember, as they're going through, they're going to be learning more, right? So you need to respond to that. The way you respond to that is not like in the moment as a teacher doing something, but it's by preparing a resource that is dynamic. In the same way that their learning changes over time and it's dynamic, your resource is changing over time. You've got to circulate while this is going on, just as, you know, I know I'm teaching you to suck eggs here, but you've got to circulate, you've got to anticipate errors, so you've got to know which mistakes they're going to make in which questions. You've got to know what to look for. So, you know, when I did those multiple choices, that's the kind of thought process I'm thinking for each of them. Insist on following your method, right? So even students who say, "Oh, I don't need to do this anymore," make them do it, make them do it. Unless, you know, you're in year 11 or year 10, you're dealing with a class that's just bossing equations, no problem. But as your students are starting out, that support is necessary. And if they don't use that support, they're going to make mistakes. But also, it's for your benefit. This is a Doug Lemov Teach Like a Champion technique called standardize the format. Standardize the format is about how easily you can spot errors and problems. So essentially, so Lemov was looking at, so Doug Lemov is an American educator. He wrote this book called Teach Like a Champion, where essentially he found the best teachers in America and looked at what they did. And he was looking at football coaches, and he noticed that if they had the students practicing like how to pass, so poor football coaches would put them in pairs and say, take a ball and go pass to each other. You'd have a kid over here and over here, and a kid over here and over here, kid over here and over here, kid here and here, here and here, and they're all kind of passing backwards and forwards between each other. And the coach would then stand here and watch these guys, and then he'd go and stand here and watch these guys, and then stand here and watch these guys, etc. What he noticed is that the best football coaches didn't do this. What they did is they said, right, get into pairs like this and pass backwards and forwards like that. And then the coach would just stand here and would be able to see exactly what's going on everywhere. So that if these guys weren't passing right, they'd be able to immediately see that there's a problem there and go and deal with it. And he called this standardizing the format, which is essentially where you make things such that it's super easy without even trying to spot an error. Let me just turn the video over. Yeah, so it's super easy to spot an error if the students make it. So what I do is, so when they're the first way I do this is by having them follow the method. If they've not laid it out neatly and nicely, then I make them do it again. I will tell them, you know, cross this out, do it again, put a line in between each step, D-E-S-C-U, go on, do it, you know how to do it. Now we've done this many times. Cross it out, do it again. But also I'll have them, for their answer, I'll have them draw a big like purple box around it so that I can just really quickly have a look. Okay, correct, done. And I don't need to like go wading through all of their work. What else have I got? Success rate of 80%. This is advocated by Barak Rosenshine's Principles of Instruction. It's kind of a bit debated about what exactly it means, but broadly, most of your students should be getting most of it right. So 80%, so either 80% of your, you know, I guess individual students should be getting about 80% correct, right? So your class average should be about 80% right in terms of the answers. The reason why that's important is because if they're getting more than that, right, work's probably a bit too easy, and if they're getting less than that, the work is probably a bit too hard and they're embedding errors. And if you notice that students are getting less than that, you've got to pull them back, pull the whole class back, right? If I notice, you know, so I let the students work and I'll stop and I'll just watch and make sure that they're working, and then I'll start going to students. I'll go to my weakest ones first, and I'll notice they made a particular error, fine. I'll then go to the strongest student and see, then I might go to like a middle student and see. But basically, if I see the same error 2, maybe 3 times, I'll stop the whole class. Stop the whole class, because it's likely, right, that if the students who I've seen have made that error is more common in the rest of the class. And even students who happen to have got it right, do I know that they've got it right this time because like they 100% know that this error is wrong? or is it just because fluke and there's a random probability that they'll get it right even if they have a particular error in their head? So don't be afraid to pull your entire class back and expose an error, expose a flaw there. There is an argument actually to going to the quickest students first, so going to your best students first. So you stop, you pause, you make sure everyone's working, and then you go to your quickest students. And this is what Bambrick Santoyo in his book Get Better Faster advocates. So you go to the quickest ones first. The reason for that is first, the point of you going around is to give students feedback, and those students, the quickest ones, will have the most material for you to be able to give feedback on. Right? If you go to a slow student who's barely put pen to paper, like you don't have much to give them feedback on. They're just thinking about it, and that's fine. They're just taking their time to think about it, like what you're going to give them feedback on. Whereas if you go to the quickest students who might have already finished a question, then you have the opportunity to give them some feedback. But also, if you go to the quickest students and they've made a mistake, then you can almost guarantee that other students in the class will have made that mistake as well. Boom, stop. Everybody stop, 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 stop. Right. Take the book up to the board, get on your visualizer or whatever. What's the error here? What's the problem? Where have we gone wrong? Why is this an error? How do we stop this error? Blah, 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 blah. Cool, cool, cool. Where are we up to? Right, so we've now done understanding the science, and we've done the first form, which means we're ready for the second form. So the first form in this case was P and T. So now we're going to do P and E, and you teach students how to solve P and E. And again, this session is not about how to teach students to substitute and rearrange and stuff like that. I linked you to those blogs earlier on. You know, use those methods and work those out. This is about then what you do in the, after that, essentially. Those have been well explored already. This is about what comes next. The second question will be very similar. Third question very similar. Fourth probably similar as well. And then you might introduce a unit conversion. So instead of saying seconds, or answer in seconds, you want your answer in minutes. And remember, in 2, 3, and 4, you might want to swap things around. So you say, how long does it take in seconds to transfer 60 joules from a 30-watt device, or whatever it is. So you might want to fiddle the difficulty a little bit. But broadly, it'll be the same form. And then so the same type, I guess, of question. And then in number 5, you want to introduce a new unit for your answer. You then want to do number 6, which goes back to your first form. So this is starting to introduce the search. Well, it's not really search. It's starting to introduce having to think about rearranging the equation and using different types of equation. It's all too easy across question 1, 2, 3, 4, and 5 to just say, right, well, I'm following the same method each time. I'm just putting this number here and this number here and this number here and this number here every single question. So you chuck in number 6, where instead of putting this number in here and this number in here, you've got to put this number in here, this number in here. You're going to move things around. And again, it's about jolting them out of that algorithm, that kind of automatic process where they're not really having to think about it. And so on and so forth. Okay, so here are some tips. Big no-no. When you're doing your worksheet, don't just chuck random numbers on there, because if you have answers that come to 1 decimal places, what are the problems? These are the problems. So what should I write? Should I write 0.47, or should I write 0.5, or should I write 0.471? Students will say it doesn't work. Why? No idea. I'll just say it doesn't work, because it gives you loads of decimal places, and like, no, so it's just not working. It has worked. It's still numbers, isn't it? No, it's just not worked. So. Leave it as the goddamn fractions of the Casio calculators that are sat on that format where everything is left as a fraction. Drives me completely mad. But it's somewhat inevitable if you've got loads of decimal places. To be honest, it happens if you've got 1 decimal place as well, but it's less likely. Oh my days. So okay, you say, right, you work it out. Blah blah blah. You say, right, the answer is 8.37. Sir, is 8.37 okay? Oh wait, so I wrote 8.38. Is 8.3772 okay? When like, you don't care, right? Because this is not a lesson about how to round, right? You want to know that they've got broadly to the right answer, they've used the equation correctly, but inevitably, yes, it's fine. Just don't bloody get. Look, it doesn't matter, okay? If it's in the range of like 8.37-ish, then it's right. So I got 8.377. Is that right? So, you want to preempt that by using really kind of straightforward numbers. I know, like, it sounds obvious, but how often do we actually put in the time to making sure those numbers make sense in advance? I know in a lot of my resources, I've just put the numbers on because I don't have the time. But in an ideal world, this is what you should do. Okay, what's next? Oh, right, here's some more tips, sorry. So when you switch to a different form, so again, there you're increasing the challenge. So for some of your students, you might increase the challenge too much and it becomes too difficult. They get the wrong answer. So sometimes it's a good idea to like add a hint, like this question is different. Make sure in your data set you get the data step right, if that's where you think they're going to go wrong, or whatever. So you're just signaling there, you're giving them support. So again, ramping up the support a bit. Because your task quantity increases, you want to give them a bit more support. Or not necessarily the task quantity, it depends how you conceptualize it, but broadly it gets harder, so you want to increase the support. Fine. What's next? Yeah, sometimes I'll give the answer. I'll often do this in the we step as well. So I say, right, your answer is 100 joules. I want to see everyone writing d'excuse and getting the correct answer of 100 joules. You can't move on until you've held it up and shown me you've got 100 joules. Great. And what that means is it's a support, basically. And what that means is that you're guaranteed for them to not start embedding a mistake. And again, it's about supporting, increasing support, lowering challenge. Yeah. So lowering the chance or the odds of them embedding an error. There's nothing worse, right, than a kid's done 10 questions. You're like, wow, well done, you've done 10. Oh, right, you've made a mistake. You've made the same mistake. They've made the same mistake 10 times. Right now, if a kid has done the same thing wrong 10 times, then that's what they're going to learn. So you need to stop that happening. So we are now done we've now done this for the first section, the first form, the second form. We're now up to the third form, which is exactly the same as what we've done before. It's the same for the second form as the second form. So you teach the third form, let them practice the third form, then introduce a unit conversion, then introduce the first and second forms, again with a hint if you think it's necessary. And then you're up to mixed forms, where you pull your class back, you go over the answers from the third form, and then you just give them a whole load of mixed questions where they've got to figure out where the data goes for each question, and sometimes it's first, sometimes it's second, sometimes it's third, and vice versa, and totally just mix up unit conversions as well. You've got to make sure you pause, review, and make it explicit, because you're forcing your students to do something different, and they might not fully realize that it's actually different yet, because essentially what you've got here is you've got a surface and deep structure problem, where so in cognitive science, surface structure is what you can see in front of you, the details of your particular question. Deep structure is like the theory and the general principles that it relies on. So in equations, right, everything we've spoken about, these 9 things of colored things, is the deep structure, and the surface is the particular question that's in front of me. And a lot of the time, students don't necessarily realize, whilst they're so obsessed with the surface and getting this particular question right, they don't necessarily realize that everything you've taught them has been about this general principle of being able to solve equations generally, and this last section is about that. And they've really got to think and go beyond just the question that's in front of them, and think about the principles, the methods, the steps that you have taught them. And I always, before I get to this step, I always do another I, we, you. So I'll say, right, let's look at this question. Okay, so this is my question. What do I need to do? Okay, well, first I'm going to write down D-E-S-C-U-S. Right, what is the data in the question? It's this. What is the equation? It's this. Okay, so like, it doesn't really matter that it's this particular question or that particular question, because I'm doing the same thing every time. I'm just taking the data, putting it into the equation, doing the substituting, the calculator, etc. Then I'll let them do a couple of examples, and then I'll let them go off and practice by themselves. Final step is called search and destroy. Search and destroy is where they have to do the search. So where you take every equation that they've ever learned up until now, and you chuck questions like that in them. So yeah, if you've just done power, definitely chuck in a couple of magnification questions. Why not? It's, again, if the deep structure is about how to solve equations, the best way to expose that deep structure is by using lots of different surfaces. Right, so if you've got surface and you've got deep, so by using loads of different surfaces that have the same deep, you're illustrating to students that the deep idea here of solving equations is the same. And again, you want to do that at every available opportunity, again, over 5 years. Right, so if you go onto test resources, right, and you download an equation sheet, you go to most of the worksheets that you can find online, even the stuff that's produced by the CogSciSci community, myself included, like loads and loads of it will just have an equation and then a practice set on that equation, and then that's it, move on to the next topic. But if you do that, you're missing a trick, because you've got to add in stuff that is from the past so that you can really expose that deep structure. That can be incredibly challenging, of course, because moving from surface to deep is like inherently challenging. I think that's probably part of the content demand aspect of our equation that we looked at before. So ways you can make that less challenging is by providing the equation. So you give magnification, say use this equation to help you solve it. That provides a nice big support. That might make it too easy, but here's one way. You can tell students where to look. So if you've given them an equation sheet, say, by the way, look at your equation sheet. Or if you're not sure how to solve this question, go have a look at, you know, the lesson, whatever, on particular date, and that will help. You can make it less wordy as well. So wordiness in question increases challenge. So this decreases the challenge. Again, sometimes this will make it too easy because it's really pulling away the, I guess, the quantity, because part of the quantity is interpreting all the different words in the equation. So this is one way of pulling that down a bit. And then hints like we saw before, so about, say, unit conversions, things along those lines. You then want to be judicious about unit conversions, decimal places, significant figures. Like I said right at the beginning, you want to communicate with your maths department. Like, honestly, like, you don't want to be teaching kids how to use significant figures. This is a waste of your time, right? The maths department are going to do it anyway, so just let them do it and steal that time back for yourself and say, right, well, you're not going to know about significant equations till, you know, the second month of year 10 or whatever. So in the second month of year 10, we'll do significant figures. So in the second term, months of year 10 or whatever, we'll start introducing significant figures, because honestly, like, it's not like it's difficult. It just takes time. So why not let somebody else do that time? And also, they are supposed to be, you know, it's their job, really, I guess. And then you also definitely want to chuck in those understanding the science questions. So those questions we did before about, you remember the faces, we would have high pressure on this face or this face, whatever, definitely interleave those as well. Because again, if the whole point is to understand the equation, like, you want to refresh that, you want to retrieve that information as well. Okay, whew, it's been what, an hour and a half, something like that. I've not really been timing. Summary equations are really, really, really challenging, and the approach needs to take both a whole curriculum level as well as a lesson level. What are the equations I want to teach? When do I want to teach them? How do I want to introduce the different aspects of them? So like I said, you don't want to do all of those 9 things every time. So it might be for your magnification, you're only doing unit conversions, but you're not going to do decimal places and significant figures, right? You're not going to do search and destroy them. You're going to wait and leave that to the next. You know, all of that is about deciding when you're going to introduce which skill, which idea, and you just got to make sure that you are limiting the challenge as much as possible. I think that the baseline assumption with equations is that the challenge is going to be high. It's a good idea to try and figure out why it's high, in terms of, is it the task quantity, the content demand, the concept is hard itself, you're not giving them enough support, the prior knowledge is rubbish. So it's important to figure out why that's difficult and what you can do to mitigate against it. And I think that's it. So this is the first slide I had up right at the beginning as a mistake, which is why when I moved on, it ended the slideshow. I am Anna Boxer, and please, please, please join the conversation online. This should go live on the CogSciSci website. Join the conversation online, either in the comments on that blog or in our email group, which I mentioned has close to 2,000 members, or on Twitter. And you can email me as well if you need anything, or have any suggestions, or if you're like, well, actually, the way you did specific capacity, I think I can do it better. I would love to see that. So please do let me know. It's been an absolute pleasure. And make sure, please, we're doing, I think, 9 of these across the summer break, so please make sure you do catch the others as well. Again, thank you for listening.